This video is a final run through of all the topics that could be assessed in the 2024 Paper 1 of AQA GCSE Physics, also known as Triple Science. There obviously isn't a huge amount of detail as I'm trying to keep the video under an hour, but all of the topics are covered. Now before we get into the physics content, a few last minute reminders. Firstly, it's important to write in black pen and to stay inside the box because your exam paper is going to be scanned, and if you don't do those two things, your examiner may not be able to see everything that you've written and give you credit for it. For all of your calculations, it's important that you use the SI units or your final answers won't make sense. Watch out for sneaky places where the exam board have, say, given you a mass in grams instead of kilograms, and you need to convert it before you complete the calculation. For all of the extended response questions, those 4 or 6 markers, it's a good idea to be answering in the form of bullet points. There aren't any marks given for writing in full sentences, and it's going to make it easier for your examiner to mark, and also it's going to save you some time. Anywhere you see the command word evaluate, the most important thing is to write a conclusion because you can't get the final 2 marks of the question without this. It's also important that you're comparing both sides of the argument or both sets of data, and where you can add value. Don't just quote values from a table, say things like this number is bigger. If you have to write a method, say for one of the required practicals, I'd really encourage you to do that in the form of a numbered list of steps, because it makes it much easier to add in something if you've missed something out, and it means that if you need to talk about repeating, then you can say, oh, repeat steps 1 to 8, and that's not going to take you very much time. At the end of writing a method, pause, read through it and say, if I gave this method to some little year 7 who'd never done this practical, would they be able to follow the steps, and would they be able to answer the scientific question that we're looking at? There are lots of working scientifically skills assessed across all 6 of your GCSE science papers, so you should be confident identifying the variables for any investigation. You should know that the difference between repeatable and reproducible is about whether you're doing exactly the same experiment and seeing the same pattern, or whether another group of scientists is doing it, or you're doing it using a different method and still seeing that same pattern. You should know that when you're making a measurement, the resolution is the smallest difference in data that you can detect, and that computerized methods like using a digital thermometer tend to be more accurate, more rapid, and more sensitive. You should also know that despite what the maths department tell you, when you're drawing a graph, the line of best fit should follow what your data does, and that means that if your data curves, your line of best fit needs to as well. All measurements contain error, which means that not every measurement you make is identical, and there are 2 main types. Systematic errors are caused by poorly calibrated equipment. So that could be something like if you have a balance where the mass always reads half a kilo lighter, and so you would solve that by just adding half a kilo to all of your data. Whereas random errors caused because of lack of precision of your equipment or just natural fluctuation around the mean, and the way that you overcome those is by taking multiple results and calculating an average. Every year after the exams, social media is filled with people who are absolutely up in arms about the fact that they were assessed on mathematical skills in their science exams. So don't forget, 30% of the marks in GCSE Physics are for these skills, and you can find a full list in Appendix 7 of your specification. For any of the base units like grams or newtons, there's a version of that unit that is 1,000 times smaller, called a milligram or a millinewton, and then a version that's 1,000 times smaller again, which is the microgram, and 1,000 times smaller again, which is the nanogram, and of course it goes the other way as well. So 1,000 times bigger would be kilo, and 1,000 times bigger than that would be mega, and then giga. And all of these conversions are by factors of 1,000. The only time that you would be using a number that is not 1,000 in one of these conversions is if you're thinking about centimetres to metres, because centimetre isn't a scientific unit, it's just a really handy unit that humans use. In 2024, like 2023 and 2022, you are going to be given a copy of the physics equation sheet. But remember, this only contains each equation in one format, and you're very likely to still need to rearrange, particularly if you're sitting the higher tier paper. The equation sheet also doesn't tell you what any of the units for these quantities are, so it's a good idea at the very start of your exam to quickly scribble these down. You should know that all forms of energy are measured in joules, and that includes work done, which is just another type of energy. And then mass needs to be measured in kilograms, and this is one of the most likely quantities to be given to you in a different unit. It's very likely that the exam board would give it to you in grams, and then you need to convert kilograms by dividing by 1,000. Then speed is in metres per second, height and also extension are in metres, and gravitational field strength is in newtons per kilogram. Temperature change is in degrees C, and specific heat capacity is in joules per kilogram degrees C. That's one of the harder units to remember, but if you know the other quantities for that equation, then you can work it out because it's just a compound unit. Time always needs to be measured in seconds, and power is in watts. Then we've got charge flow in coulombs, current in amps, potential difference in volts, because of course its other name is voltage, and resistance in ohms. We've already covered all of the quantities in the first two of these equations, but then we go to density, and this is a strange one because it's one of the only examples where the exam board may not use the SI units for a particular quantity. We would normally expect to measure density in kilograms per metre cubed, and therefore have mass in kilograms and volume in metres cubed. But you may also encounter situations where the exam board give you the mass in grams and the volume in centimetres cubed. And then because density is just a compound unit, you would go on and use those two units to make your new units for density, which are grams per centimetre cubed. Specific latent heat is measured in joules per kilogram. And then finally, just for the triple physicists, we get pressure times volume equals a constant, and pressure needs to be measured in pascals and volume in metres cubed. The first topic in Physics Paper 1 is energy. You should know that a system is an object or group of objects, and a system can store energy, and there are a number of different ways it can be stored. It can be a magnetic store, a kinetic store, which means a moving object, a thermal store, so a hot object, a gravitational potential store, where an object has been raised against the action of a gravitational field, a chemical store, where the energy is stored in bonds, elastic potential stores, where an object has been stretched, an electrostatic store, where we've got attraction between positive and negative objects, and finally a nuclear store. It's possible for energy to be transferred between those stores in four ways: by heating, because there's a temperature difference, mechanically, electrically, and by radiation. You can't store energy as a light or a sound, but you may have energy being transferred through radiation, of which light and sound are types. A closed system is where we have a situation where no matter, so no stuff, and no energy can get in or out. Within a closed system, you can't create energy and you can't destroy energy, you can only transfer it. So if we know how much energy is stored at the start of a scenario, then at the end we must have the same amount. It might just be stored in different ways. So for instance, you might start out with a chemical store and finish with a thermal store, but the total amount of energy is the same. Energy is always measured in joules, and you want to be writing joules with a capital J. You're expecting to see lots of questions in GCSE Physics where you're asked to use one of these equations in order to calculate an amount of energy. So for instance, here we're asked to calculate the GPE when an object is lifted up. So our first step is to write out the equation, and then our second step is to write down which number each letter represents. So here the mass is 5 kilograms and the gravitational field strength is 9.8 and the height is 1.5 meters. And as we've said, we need to watch out for the height being given in centimeters instead, or the mass being given in grams instead, because we would need to convert those before we do the calculation. Then we multiply those numbers together, and then of course we need to write our units afterwards. Our next energy store is kinetic energy, where we have a moving object. So things to watch out for with this equation are that the squared sign only refers to the velocity. It's not everything before that being squared, it's just that final velocity or speed. Again, a typical question might ask you how much energy has been stored. So you'd write out the equation and then write out the numbers here. If you don't have a fraction button on your calculator, it's fine, you just use 0.5 instead. So I would multiply those numbers together, making sure that I'm only squaring the 5, not everything else, and that would give me an answer of 250 joules, and again it has a capital J. Again, in the elastic potential energy equation we have a squared sign, and again it only refers to the final letter. And again here you need to watch out for the fact that extension needs to be in meters, not anything else, in order for the calculation to work. It's worth pointing out here that for some questions you may need to calculate one of the other terms in this equation, such as working out the spring constant. Hopefully you're really confident rearranging equations, but actually even if you're not, you can still answer these questions, because for reasons best known to themselves, when AQA write the mark schemes, they actually prefer you to substitute first. So if I had a question that asked me about the spring constant, which is K, then what I could do is I could put in all the numbers I know and then solve for K. So I know that it's storing 4,500 joules of energy, and that's going to be equal to half times K, the spring constant that I want to work out, times 3 squared. So if I simplify that, I get 4,500 is 4.5 K, and then if I divide both sides by 4.5, I get an answer that K is 1,000, without having me do any rearranging at all. The next topic is specific heat capacity, which comes up in two different parts of the specification. Now, capacity is a concept that you were first introduced to in primary school, probably in year 2, when you learned that different objects could contain different amounts of liquid. So capacity is all about the ability of an object to take something in. And then heat capacity is about the energy that a substance absorbs when it's changing temperature. And specific heat capacity is the energy that 1 kilogram of a substance needs in order to raise its temperature by 1 degree C. There's a required practical that looks at how much energy it takes to heat up different objects or different substances. And in order to carry out that required practical, we have this calculation. And this one can throw people a little bit because it's got some extra symbols in it. So the triangle sign is called delta and it means change. So delta E isn't two separate quantities, it's the change in energy. And likewise, delta theta is the change in temperature. Like density and also speed, this calculation is quite a nice one in that the units for the tricky bit actually tell you what to do with the calculation. So if you want to calculate specific heat capacity as the subject, you can see that the units for specific heat capacity, which they will probably give you in the question if they were asking you to work it out, are joules divided by kilograms degrees C. So if you have to work out specific heat capacity, you take the joules, which is the amount of energy, and you divide it by the mass and by the temperature. Watch out for the fact that you do need to have the change in temperature. So they might give you a starting temperature and an ending temperature, and you need to work out what the difference between those two numbers are. Also, again, the mass needs to be in kilograms. So if it's not, divide by 1,000 to get it into them. The idea of the required practical for this topic is that you're given either a metal block or a container of liquid, and you're trying to work out what the specific heat capacity is. In other words, how much energy would it take to heat up 1 kilogram by 1 degree C? Firstly, you're probably going to have a metal block with 2 holes in it, or you might be given a beaker of liquid. You have a balance because we want to know how much energy it takes to heat up 1 kilogram, and your block might not have a mass of a kilogram, so we might need to adjust our calculations to take account of that. There's some insulation because the experiment only generates accurate data if all of the energy that's being given out or transferred by the heater is going into the block or into the liquid. Now, obviously that's not realistic and some of it is going to dissipate and go into the surroundings, but we want to minimise those energy losses as far as possible. So you need to insulate the thing that you're heating up. We've got a thermometer so we can identify how much it is heated up by, and realistically we're not going to heat it up by just 1 degree C because making small measurements reduces the precision of the final value. So to increase the accuracy of our results, we're going to heat the block up by maybe 10 or 20 degrees and then divide the amount of energy by 10 or by 20 to take account of that. My pipette here is because the thermometer won't make good contact with a metal block. So in order to get a proper temperature reading, you add a tiny bit of water and that will come up to temperature with the block, and then what you're doing is taking the temperature of the water. We need some kind of electrical heater to heat up the block, and then the last 3 are for us to calculate the amount of energy that's been transferred. So you measure the potential difference using the voltmeter and the current using the ammeter, and then those 2 readings together can be used to work out power, and then once you know the power you can use the stop clock to work out the amount of energy transferred. Alternatively, you can also use a joule meter. Now they are not mentioned anywhere in the specification, but they did come up in the 2022 exams, so presumably it's fine to talk about using that piece of equipment instead, and that will directly give you a result of how much energy has been transferred. The final topic in this 1.1 energy section is power, which is the rate at which energy is transferred or work is done. In other words, how quickly does energy move between stores? And the more powerful an appliance is, the faster it can do work or transfer energy. Typically early in the paper, you might be asked to calculate the power if an appliance like a kettle transfers a certain amount of energy in a certain amount of time. So here I would say that the energy is 2000, and I can tell that's energy because there's a J after it for joules, and I would divide that by the time in seconds and get an answer of 500 watts. Now you'll notice here that to get my answer, I did energy in joules divided by time in seconds. So we can also say that a watt is exactly the same thing as a joule per second. It's just that rather than using that compound unit, which is quite nice and useful, like with lots of things in physics, we name it after a dead white man instead. Then we move on to section 1.2, and the first thing we need to know about is efficiency, which is the proportion of energy that's been usefully transferred. It can be expressed either as a decimal or as a percentage. We've already said that conservation of energy describes how we must have the same amount of energy at the end as at the start, and that means that my useful and wasted energy transfers must add up to be the same as my initial starting amount of energy. So for instance here, my light bulb might transfer 1,000 joules of energy, but 100 joules of that energy is transferred as light radiation, and the other 900 joules is transferred wastefully by a heating pathway. And that's not what I want to do. So my light bulb would only be 10% efficient, or we could also say it has an efficiency of 0.1. There are two equations for efficiency, but they're basically just the same, only one of them is expressed in terms of energy and one in terms of power. You might get a question that asks you where the energy ends up when it's wasted, and there will almost always be a transfer to a thermal store in the surroundings. And when the energy has spread out so far that it's not useful anymore, we just can't use it, we describe that as dissipating. For the higher tier, you should be able to discuss a number of ways in which we can reduce the wasted energy. We can reduce heat loss by insulating something, which is particularly relevant if you're thinking about houses and how they might have loft insulation or double glazing to help them be insulated. We can also talk here about the thermal conductivity of a material. So if you're looking at different kinds of brick, just regular brick versus breeze block, then the higher the thermal conductivity is, the higher the rate of energy transfer by conduction. So in other words, the better conductor is, the faster it conducts. You can also reduce wasted energy by reducing drag by streamlining, which is particularly relevant if you're thinking about boats or cars or any other vehicle. We can also reduce wasted energy by reducing friction, so that might be using wheels or lubricating moving parts. If those frictional forces aren't reduced, then they can cause energy to be transferred by heating. So speaking of insulation, we have another required practical, and this is very similar to the required practical that you do in the waves topic for paper 2. So we're looking at energy transfers, but this time, rather than thinking about different surfaces, we're thinking about different insulation. So we're going to start out with a series of metal cans or hollow metal cubes, or you could even do this with glass lab beakers. And they need to be the same dimensions and the same material, but you're going to wrap each one in a different kind of insulation. And then you may have one can which is described as a control, which is the one that you haven't insulated at all. You're going to fill them up with hot water, and the volume of water would be a control variable. So either you're going to fill them all completely up to the brim if they're identical cans, or you could use a measuring cylinder and measure out the same volume of water for each can. You put a thermometer into each can and wait for those thermometers to reach their maximum temperature, because it'll take them a little while to give an accurate reading. And then once the temperature starts going down, you start a stop clock, and maybe every minute for 10 minutes, you record the temperature. And based on this, we can see that the temperature that drops the least, that must be the can that is the best insulated. The final part of this energy topic is about national and global energy resources. You should be able to distinguish between renewable energy resources, which are being generated faster than they're being used, and non-renewable energy resources, which are being used faster than they're being generated. All of these energy resources can be used in a variety of ways, including transport and heating, as well as electricity generation. For each energy resource, you should be able to discuss the advantages and disadvantages. This often comes up as an extended response question where you're asked to compare the advantages and disadvantages of two of these different energy resources. So you want to think about things like, are they renewable? Are they expensive? Do they have carbon dioxide emissions, which can then link to global warming? Are they reliable? And are there geographic restrictions on where you can use them? Then also for nuclear power, you want to think about how you would dispose of the radioactive waste and the risks associated with nuclear accidents. The second topic in AQA GCSE Physics Paper 1 is electricity, and the first thing you should know is how to draw all of the different circuit components. Of course, it's important that when you draw a circuit, you're using a ruler for your wires and you're not leaving any gaps in the wire. One symbol to watch out for is your resistor, because often people draw their lines first and then draw the rectangle over the top of it, and that would mean that you're actually drawing a fuse rather than a resistor. There are lots of different equations for electricity, and although you are going to be given all of them on the equation sheet, it's worth bearing in mind that for extended response questions in physics, you're sometimes asked to stack more than one equation together. So if you do get a longer question, probably 4 or 6 marks, where you're asked to calculate something and you just can't see from the question where you're meant to start, what I would do is find the quantities that are in the question and then find an equation that uses those two quantities to work out a third thing, and work that out, because you can almost guarantee that will be worth some of the intermediate marks. And once you've got that far, you might be able to see how to use the remaining information to get to a final answer. You should be familiar with the idea that current is the speed of the flow of charge around a circuit, and potential difference is about how much energy is being transferred by a component. Now, the thing to remember with current is that even though we now know that the current is the flow of delocalized electrons, when the idea of electricity was first described, scientists didn't know about electrons, and so they thought they were positive particles. When they first started describing electrical circuits, they described current going the wrong way, and so even though we now know that it's electrons, we still continue to talk about this, and it's what we call conventional current. The first electricity required practical is looking at the IV characteristics, in other words, the current and the potential difference of a wire of different lengths, and also resistors in series and parallel. So basically for each one of these you need a simple circuit containing an ammeter, which needs to be in series because otherwise it won't work, and a voltmeter, which needs to be connected in parallel. So remember that the voltmeter is measuring potential difference, and so in order to measure the difference between the two sides of the wire, it needs to be connected on both sides of the wire. When you're doing this practical, it's important that you don't let the wire get too short, because then the current will get really high and the wire will get really hot. So that's a safety concern there. In the second electricity required practical, we're still measuring the current and potential difference, but this time we're looking at a number of different components. So this could be an ohmic conductor, in other words, a wire or resistor at constant temperature, and a filament bulb, and also a diode. You might be asked to draw a circuit that would allow you to do this, so again it's really important that the ammeter is in series and the voltmeter is in parallel. You could change the potential difference by using, say, a power pack and just changing it on there, but the other thing you can do is to include a variable resistor within the circuit, and then as you increase the potential difference across that, you're going to decrease the potential difference across the other component. Once you've completed the practical, you'll be able to draw these three IV graphs. So we've got potential difference on the x-axis, and as we increase that, we see what happens to the current, and we plot that on the y-axis. First of all, we have an ohmic conductor like a wire at constant temperature, and as we increase the potential difference, we see that current also increases in a directly proportional manner. So we have a straight line graph that passes through the origin 0, 0. The filament lamp looks a little bit different. It's this slightly S-shaped curve, and the reason for that is that the temperature is not remaining constant. So as we increase potential difference, that increases current, and as we increase current, that increases temperature, and as we increase temperature, that increases resistance. So even though the current is still going up as potential difference goes up, it starts going up by smaller and smaller amounts. And then finally we have the diode, and there are two things to note about this graph. The first one is there is nothing below the x-axis, and the reason for that is that the diode will only allow current to flow in one direction. The second thing to note is that if you only have a very, very small potential difference, then you still don't get the current flowing. So initially there's a little bit of sort of insulation, and then when you give it a higher potential difference, then current can begin to flow. So the graph is going to track the x-axis for a little bit before it goes diagonally upwards. Next, you should be familiar with light-dependent resistors and thermistors. Now watch out because these graphs look similar, but there are key differences. We no longer have current on the y-axis, instead we have resistance. And what these graphs tell us is that a light-dependent resistor resists less as the light gets brighter. So you could use it to turn on a radio in the morning. As the sun comes up, the resistance goes down, the current starts to flow, and your radio switches on. And then for a thermistor, as the temperature increases, the resistance gets less. So that's opposite to a wire. In a series circuit, there is only one path that the charges can follow, whereas in a parallel circuit, there's a junction where the current splits, and some charges go past one light bulb and some charges go past the other light bulb. For series and parallel circuits, you need to be able to discuss both the current, so how quickly the charges are moving, and the potential difference, the amount of energy that's being transferred. If we think about the series circuit first and current, we've said that current is about how many charges pass a particular point per second, and the image you want to have in your head is that this is like a traffic jam. There are no gaps, and if one charge moves forward, the ones behind it will also move forward, and everything has to move at exactly the same speed. So because there's only one loop and all of the charges are going the same way, they're all going to go at the same speed. So if we measure the current anywhere in a series circuit, it will be exactly the same, and I can put my ammeter wherever I like. Now the parallel circuit is a little bit different because the charges are still going nose to tail like they're in the traffic jam, but when they get to point A, they're going to split. So if those branches are identical, then half of the charges will go one way and half of them will go the other way. Now the branches might not be identical, and if that's the case, then different numbers of charges are going to go each way. So it could be that 2/3 of them go down one branch because that branch contains less resistance, and 1/3 of the charges go down the other branch. But we're always going to have a situation where the current in the two branches adds up to be the same as the total current before the split. Now, whereas for current, it's the same everywhere in series and it splits in parallel. For potential difference, it's the other way around. In the series circuit, the potential difference is going to be split between the two components, whereas in the parallel circuit, each component gets the full potential difference. And that's why the light bulbs in a parallel circuit are much brighter. Finally, if we think about resistance, you should be able to describe that in a series circuit, to work out the total resistance, you just add up the individual resistors. So if I have 3 2-ohm resistors in series, then the overall resistance of that circuit is going to be 6. Whereas in a parallel circuit, the total resistance is going to be less than the resistance of the smallest individual resistor. To actually work it out, we say that 1 divided by the total resistance is going to be 1 divided by each of the individual resistances. But basically, the most important thing is that when you add all of those up together, you're going to find that the overall resistance is less than any of the individual ones. The British main supply of electricity is AC, which stands for alternating current. So alternating current is current that repeatedly changes direction. In the case of the main supply, 50 times per second. This helps to maintain power, and it's also important because the transformers used in the national grid will only work with an AC supply. In contrast, direct current, which you get in a simple circuit with a cell or a battery, is current that only flows in one direction. Most appliances are connected to the main supply using a 3-core cable, which attaches to the supply using a 3-pin plug. The outside of the plug is made from rigid insulating plastic, and the pins are made from an alloy of copper called brass. As you know from chemistry, alloys are harder than pure metals, so this stops the pins bending when you put it into the wall. You need to know the names, locations, colours and functions of the 3 wires. The live wire is the brown wire, and you can remember that it goes on the bottom right because bottom right is BR and so is brown. The live wire carries the alternating potential difference from the main supply. The neutral wire is blue and it sits on the bottom left of the plug, BL for bottom left, BL for blue, and it completes the circuit. It has a potential close to 0, which is earth potential. The earth wire has green and yellow stripes, and it's a safety wire to stop the appliance becoming live if there's an electrical fault where the live wire touches the metal casing. And then the plug also contains a fuse, which will melt if too much current flows. It's really important that you talk about it melting, not saying that it blows up. When we're just talking as normal humans, not physicists, we often say that the fuse blew, and so this means that students write in the exam that it exploded, and that's not true. It just melts because it gets too hot. A fuse is going to have a rating based on how thick it is, so typically in the UK we use 3 amp fuses or 13 amp fuses, and the idea is you want to use a fuse that has a rating slightly higher than the normal current. So say if I had an appliance where the normal current flowing through it was 11 amps, then a 13 amp fuse would be appropriate for me to use because if there was a surge, it would then melt. I wouldn't use a 3 amp fuse because that would melt just when the appliance was working normally. The national grid is a series of cables and transformers which links power stations where electricity is generated to domestic customers like houses. The transformers are important because they allow this to be a really efficient process. In those central cables that run between pylons, the electricity is travelling with a really high potential difference. And the reason for that is that there are 2 ways that we can get the amount of power that we need to our domestic customers. Firstly, we could have a really high current. The electrons would be moving really fast. And if that was the case, the wires would end up heating up and resisting, and we would lose a lot of that energy to the surroundings. It would dissipate into the atmosphere. So high current doesn't really work for us because it wastes a huge amount of energy and therefore costs a lot of money. The alternative is to have this really high potential difference, but we don't want that high potential difference in the power station and the domestic supply because high potential difference is really dangerous. So what you have is, firstly, between the power station and the cables, a step-up transformer, which increases the potential difference. And then we have this really high potential difference going through the cables, and then at the other end there is a step-down transformer, which is going to reduce the potential difference so that it's safe for consumers again. So we've now reached the part of the electricity topic that is just for the triple scientists. So if you're watching this video, even though you do combined science, you need to skip on a little bit. When certain insulating materials are rubbed against each other, they become electrically charged. And the reason for that is that when you're rubbing them together, the force of friction is removing electrons from one and moving it onto the other. Those electrons are negatively charged, so the material that gains the electrons will also become negatively charged, and the material that lost the electrons will become positively charged by the same amount. Now, when we've got 2 objects that have different electrical charges and they're brought close to each other, they exert a force. And what that force is going to depend on whether the charges are the same or different. So if we have 2 objects that have the same charge, then they're going to repel each other, whereas if we have two objects that have different charges, then they will attract together. And these are examples of a non-contact force. Now we reach the portion of the electricity topic which is just for the triple scientists. A charged object will create an electric field around itself, and that field is a region where if we brought another charged object into that region, it would experience a force. So that could be an attractive force if they have opposite charges, or a repulsive force if they have the same charge, but either way it's a non-contact force. The objects don't need to actually touch each other. So that electrical field around the object is going to be strongest where you're closest to the object. So just like how a gravitational field, you know that as you're close to the surface of the Earth, it's very, very strong. And as you move up and up through the atmosphere, it gets gradually weaker until you get into space. And at that point, you can't feel the gravitational field of the Earth anymore because you're too far away. So if we bring another charged object in, it will experience a force, but the further away from the object is, the weaker that force is. You need to be able to draw the electric field pattern for isolated charged spheres. In other words, we imagine that an object was purely positive or purely negative and say, well, how would the electric field lines look for those? So as you know, your electric field lines are always going to be drawn from the point of view of what would happen to a positive object. So if you've got a positive object, then the field lines are all going to be going away from that positive object. And if you've got a negative object, then the field lines are all going to be coming in towards that negative object. You also need to be able to describe why sparking happens. So this could be in terms of something like discharging a Van de Graaff generator or, just lightning happening. So basically it's where we have an earthed conductor which approaches the charged object. And then very, very quickly the charges jump across the gap from the charged object to the earthed conductor and the object discharges. And that happens in a fraction of a second. The third topic in AQA GCSE Physics Paper 1 is the particle model of matter, which starts off with our three different states of matter, which you should be able to recognise or draw. Later I've drawn these in a more traditional way with the boxes the same size, but I don't want to give you the impression that the number of particles changes during a state change because that's not accurate. In the solid, the particles are packed together in a regular structure, whereas in a liquid they're still close together and touching. There aren't any gaps that you could push a particle into, but they're no longer in a regular structure. And in a gas, the particles are separated by large distances. You need to be able to talk about the forces between them. So in a solid, there are really strong forces holding the particles in place. And then in a liquid, those forces are a bit weaker, so the particles maintain contact and they can't individually fly off, but the forces are weaker than they are in a solid, and in the gas there are really, really weak forces. In the solid, the particles are moving, but they're vibrating in fixed positions, whereas in a liquid, the particles are able to pass each other, and in a gas, the particles are constantly randomly moving. And then in terms of how this affects the properties, it's difficult to change the shape of a solid because of those strong forces and because the particles are regularly packed together. Liquids can change shape quite easily if they are poured into a different container, but they are virtually incompressible. So if you put some water in a syringe, you can't squash it because there aren't any gaps for the particles to move into, and that's how hydraulic brakes work. Then a gas can easily expand to fill a space, and therefore it's also easy to compress because it's got big gaps between particles. You should be able to name all of the state changes, so melting, freezing, boiling, evaporating, condensing, and of course the one that people forget is that some things can sublime, which is where it turns straight from a solid into a gas. It's very rare, but carbon dioxide does it, and so does camphor wax. You should be aware that in all of these state changes, you're not going to have any change in mass because you've still got the same particles that were there at the start. And these are physical changes, so we're not making new chemicals that weren't there before, and if we reverse the heating or the cooling, then we could reverse and go back to the original substance with the original properties. We can link these states of matter to density, which is a measure of how much mass is contained within a unit volume of a substance. In the vast majority of cases, the particles in a solid are closer together than in a liquid, and that means that within the same volume, say a metre cubed, you're going to be able to fit more particles. And since those particles have the same mass, if there are more of them, then you've got more mass per unit volume, and therefore the density is higher. So say if I've got a metre cubed of a metal and some water and some chlorine, you can see there that the masses are gradually going down, and so are the densities. This leads us nicely onto our next required practical, in which we determine the density of regular and irregular solid objects and also liquids. The calculation to work out density is mass divided by volume, and it's one of these nice ones where the units give you the equation and vice versa. So whether we're looking at a regular solid or an irregular solid or a liquid, you need to know what the mass is, so you're going to need to use a balance, and you also need to know what the volume is, and that's the bit where it's different for the three different parts of the practical. For a liquid, you're going to determine the volume using a measuring cylinder. So you put your empty measuring cylinder on the balance and tear the balance so that it acts as if the measuring cylinder is not really there, and then you fill up the measuring cylinder with a certain volume of liquid, and the bigger your volume is, the more precise your data will be, and then you record the mass and you read the volume off the measuring cylinder. For a regular object, you can measure the length and width and depth using a ruler, or to be even more precise, you could use calipers as I've shown here. Then you can work out the volume by multiplying the length by the width by the depth, or if you're given a cube, then you could just be given one length and you would use that same length 3 times. And then you calculate density by taking the mass that you measure, again using a balance, and dividing it by that volume. And then for an irregular object, you're going to need to use a piece of equipment called a displacement can, or you might call it a eureka can. So you fill this can up completely with water until the water is coming out of the spout, and then you put your object into the can and completely submerge it. And as you do that, more water will come out, and the volume of that water will be equal to the volume of the object. So you catch that displaced water in a measuring cylinder, and then you can measure the volume just by reading it off in exactly the same way that you did for the liquid. The energy that's stored in a system by the particles is called internal energy, and everything has internal energy even if it's not moving right now. It's made up of two things: the total kinetic energy of the system, in other words the particles that are moving around, and the total potential energy of the system. As you're heating a substance, the energy stored within the system will increase, but this isn't always reflected by an increase in temperature. If we take some ice and we heat it up, we see a graph that looks like this, which might come as a bit of a surprise, because you might expect the temperature to just go up all in one nice straight line. So to begin with, we have this flat line here where the ice is melting, and another flat line here where the water is boiling. Whenever the substance is going through a state change, the temperature doesn't change. You can almost think of it like the substance can't multitask. Either it can get hotter or it can change state, but it can't do both at the same time, assuming that it's a pure substance. So the red bits of the graph here represent places where the energy is going into the substance and it's making the particles move faster. So if it's a solid like ice, then the particles are vibrating faster on the spot, and then if it's a liquid, the particles are moving faster past each other, and so the temperature is increasing. If I want to know exactly how much energy it's going to take to do this, then we need to know the specific heat capacity, which we met earlier in the energy topic, and that tells us how much energy is needed to raise the temperature of a substance by 1 degree C. Then the green bits of my graph here are where the state changes are happening. And here, instead of that energy increasing the kinetic energy of the particles, it's increasing the potential energy of the particles. And that's where my state change happens. And if I want to know how much energy then that's going to take, then I need to know about specific latent heat, which tells me how much energy is needed to change the state of 1 kilogram of a substance. Now that's not going to be the same amount of energy for melting as for boiling, so we have slightly different names for these. We have the specific latent heat of fusion when a substance is melting, and the specific latent heat of vaporization when it's turning into a gas. Again, this is an equation with quite sensible units in that energy is going to be measured in joules and mass is measured in kilograms, so therefore specific latent heat is in joules per kilogram, which is nice and easy to remember. You should know that the molecules of a gas are in constant random motion, and the temperature is related to the average kinetic energy of the molecules. In other words, if the temperature is hotter, then the particles are moving faster. Provided we're working at constant temperature, then pressure and volume of gas are inversely related. This means if you've got a balloon and you keep it at constant temperature and you stretch it out so that the volume is double what it was before, then the pressure inside will halve. So say I start out with a pressure of 100,000 pascals and then I stretch my balloon so its volume goes from being 1 meter cubed to 2 meters cubed, then the pressure will drop to 50,000 pascals. And then likewise, if it stretched out to 4 meters cubed, it would drop to 25,000. And likewise, if I stretched it out to 8 meters cubed, then the pressure would drop to 12,500. But we're only going to have that lovely mathematical relationship in a world where the temperature isn't affected. So in the real world, as the volume decreases, the temperature would rise and vice versa. We can apply this to real life scenarios like pumping up your bike tyres. When you're inflating the tyre, you are doing work, you are putting in energy, and that's provided to the particles of the gas as kinetic energy. So since temperature is really a measure of the average kinetic energy of a substance, if you increase the kinetic energy by putting in a lot of work, then you increase the temperature of the gas. The final topic in AQA GCSE Physics Paper 1 is about atomic structure and radiation, and the first part of this is common content with Chemistry Paper 1. You need to be able to describe this nuclear model of the atom. There's a small dense nucleus containing protons and neutrons surrounded by electrons which are orbiting at fixed distances, which we usually call shells. You should be able to describe the relative masses and relative charges of each one of these subatomic particles. It's important where you see the word relative that you're answering in the form of a number and not just saying positive or negative or neutral. You are allowed to say that the mass of an electron is very small because that's what the specification says, but if you do know a numerical value for it and you want to give that, then that is also fine. In terms of the numbers of these particles, the bottom number for an atom is the atomic number, and that tells you the number of protons, which will be the same as the number of electrons in an atom. Then the mass number tells you how many particles there are in the nucleus. You should know that the radius of an atom is about 0.1 nanometers, which can also be expressed as 1 times 10 to the minus 10 meters, and only about 1/10,000th of the radius of the atom is the nucleus. Now, the reason this is relevant is that when we talk about radioactivity, it tends to be different isotopes of elements that we're interested in. Isotopes are atoms of the same element that have the same number of protons and different numbers of neutrons. If you've been revising from something other than an AQA textbook, you might have also seen this defined in terms of atomic number and mass number, but your exam board wants you to define it in terms of subatomic particles, and they'll often say in the question, give your answer in terms of particles in the atom. So you must be talking about protons and neutrons in your answer. The section about the model of the atom is basically getting across this idea that scientists do experiments, they collect some data, and then they update their model in light of that data. We start out with the British scientist John Dalton, who described atoms as being solid, indivisible spheres. He thought they were like a billiard ball and you couldn't cut them in half, they were just solid. Then J.J. Thomson discovered the electron and he developed the plum pudding model. This had negative electrons set in a ball of positive charge. Then there was Ernest Rutherford and he did the alpha scattering experiment. He's the one scientist where you actually need to know the details of the experiment that he did. So he took this very thin layer of gold foil and fired alpha particles at it. And he found that the vast majority of these went straight through, and this was evidence that the vast majority of the atom was empty space. He also found that a very small proportion of the alpha particles were deflected back, and this was evidence for two things. Firstly, it told us that at the centre of the atom there was a small, dense nucleus. And secondly, that nucleus had a positive charge because the alpha particles had a positive charge. So if they were repelled, and we know that opposites attract and like charges repel, therefore the nucleus must be positively charged too. Niels Bohr did some calculations and said that electrons orbited the nucleus at fixed distances, which we now call shells. And then later various people did experiments which corroborated that. Then later on again, there were experiments that led to the idea that the positive charge of the nucleus could be split up into smaller particles, which all have the same amount of positive charge, and we call those protons. And then finally, in 1932, James Chadwick provided the evidence to show that there were also neutrons in the nucleus, and those, of course, were really important because they told us about the existence of isotopes. You need to know that some atomic nuclei are unstable, and those unstable nuclei will then give off radiation as they're changing to become more stable, and this is a random process called radioactive decay. When we say it's random, what we mean is we can't predict which nucleus is going to decay at which time. We just have to wait and see which order they go in. Now, as that decay happens, and as the alpha particles or beta particles or gamma rays are given off, we describe the rate at which that decay happens as activity, and this is measured in becquerels, and you measure it with a piece of equipment called a Geiger-Müller tube or a Geiger counter. All of these different kinds of radiation ionize, and what that means is that they turn other atoms into ions by removing their electrons. The first type of radioactive decay you need to know about is alpha decay. An alpha particle is made of 2 protons and 2 neutrons. In other words, it's the same thing as a helium nucleus, so just a helium atom that we've ripped the electrons off. I start off with my parent nucleus of my unstable isotope, and then an alpha particle breaks off and it's released, and what's left behind we call the daughter nucleus. Now this is going to be a completely different element because it's lost 2 protons. It's also going to be 4 atomic units lighter because it's lost 2 protons and also 2 neutrons. Alpha particles are very ionizing. In other words, they're great at turning other atoms into ions. They're not very penetrating because they're so big that they're really easily stopped, and they have a short range in air for the same reason. They collide with molecules in the air, and this stops them from travelling further. They can be deflected or pushed to the side by an electromagnetic field, and they can also be stopped by a thin layer of paper. Beta decay is also a particle. This time it's a fast-moving electron, and this often confuses people because we're talking about a nucleus, so why would there be any electrons? The best way to think of it is to imagine that a neutron is made out of a proton with an electron stuck to it. One of these neutrons is going to turn into a proton, and in the same process it's going to release that fast-moving electron, and that's the beta particle. Again, this element is going to turn into a different element because it's now got one more proton than it had before. Beta particles are less ionising than alpha particles, both because they're smaller and because they've got a slightly lower charge. It's one negative electron as opposed to two positive protons. However, they are more penetrating. They're smaller, so they can get further before they're stopped. They have a medium range in air, and they are still deflected by an electromagnetic field, but they'll be pushed in the opposite direction to an alpha particle, and they can be stopped by thin aluminium foil. Finally, we have our gamma radiation. Now, this is not a particle, it's a transverse electromagnetic wave, and we see it being released at the same time as an alpha particle or a beta particle. But because it's not a particle, when it comes to writing equations, there isn't any difference between the parent nuclei and the daughter nuclei. The gamma ray being released doesn't change which element something is, and it doesn't change the mass of the nucleus either. Gamma rays are even less ionising than beta particles, and they're even more penetrating. They have a huge range in air, and they can basically move infinite distances in a vacuum, and they're not deflected by an EM field, and they can only be stopped by using thick lead. So to summarise what we've said so far, the alpha particle can be stopped by paper, the beta particle goes through paper but can be stopped by aluminium foil, and the gamma radiation keeps on going until it meets thick lead. For GCSE, you don't need to be able to predict what the daughter elements are from nuclear equations, but what you do need to be able to do is to make the atomic numbers and the mass numbers balance. For an alpha particle, this is relatively straightforward. Radium-219 has a mass of 219, and the alpha particle has a mass of 4, so therefore polonium must have a mass of 215 because the two sides of the equation have to add up to be the same as each other. And then likewise, radium has an atomic number of 86, so if the alpha particle has an atomic number of 2, then polonium must have an atomic number of 84. The beta particles tend to be where people fall down. The mass is quite straightforward because the mass of an electron, at least as far as this equation is concerned, is 0. So the mass of the nitrogen isotope remains 14. But the really common mistake we see is that people will do 6 minus 1 and end up with 5 for the atomic number, which is not correct. So think about it, you have to have the two sides of the equation balancing. So 6 is equal to something, take 1, and the something of course is going to be 7. So just watch out for that because that's a really common mistake in the exams. Next we talk about half-life. We've said that radioactive decay is a random process. We don't know which particular nucleus is going to decay, but we do know that the rate of decay is pretty much constant. So half-life is the time taken for either the count rate, which is measured with a Geiger-Müller counter, to decrease by half, or for half of the number of atoms in the sample to decay, because those are going to be the same amount of time. Now, there are two ways that you can be presented with a question about this, either in the form of a graph or in the form of some numerical data. If I have a graph, the y-axis could represent activity or count rate or the number of nuclei, and I would handle any of those graphs in exactly the same way. Let's say that my initial activity is 20,000 becquerels. To work out what the half-life is, I'm going to see how long does it take for the activity to fall to 10,000. So in other words, for it to reach half. So I could then read off my axis that this took 5 seconds or 12 years or whatever it is. Here I've just marked it with t. Now the interesting thing is you don't actually have to start at your y-axis because the rate of change will remain constant. So I could start at 10,000 and it would take the same amount of time for it to reach 5,000, and likewise it takes the same amount of time to reach from 5,000 to 2,500. The only advantage with starting where your graph hits the y-axis is it means that rather than needing to do a subtraction of your x-axis numbers, you can just read off the number that you've got to. Now, the alternative here is that they give it to you in terms of numbers. So say I've got a sample where I start off with an activity of 64,000 becquerels and it's dropping to 4,000 becquerels. And we want to work out how long is the half-life. So the first thing we want to do is to write out the numbers and half the activity. So I start off with 64,000 and I half that to 32,000 and so on. And I would really strongly encourage you to draw arrows between them, and here's why. Lots of times people will look at these numbers and then go, ah, that's 5 half-lives. and then they'll do the calculation and come out with the wrong answer, because it's not 5 half-lives, it's 4 half-lives. So drawing the arrows helps you to remember to count the arrows, not count the numbers. So I've got 4 half-lives, and I said that 4 half-lives is 24 days, so therefore what's 1 half-life? If I divide by 4, I'm going to get 6 days, and that's my answer. Next, we need to talk about contamination and irradiation. Radioactive contamination is where there are unwanted radioactive atoms that have been stuck onto something else, so they've made that other object radioactive. And the risk there is that at some point those radioactive atoms are going to undergo decay, and therefore whatever object they're stuck to would be exposed to that radiation. Now, the exact level of hazard is going to depend on the half-life of those nuclei and also the type of radiation that's being given out. So if they've got a half-life of 10,000 years, then even if they're stuck on a person, that person is probably quite safe. Whereas if the half-life is a few seconds, they're definitely going to be exposed to radioactive decay. Now, irradiation is different because it's not the radioactive parent nuclei that are on you or on the object that's being irradiated. What's happening is that the object or the person is being exposed to the alpha radiation or beta radiation or gamma radiation that's being given off. Now, that could still be hazardous to your health in that it might ionise your DNA and lead to mutation and ultimately cancer. But that object or that person is not becoming radioactive. And if they move away from that radioactive source, there's no further risk of injury. We often use irradiation to make sure that we're killing off any bacteria on something. So for instance, it's used to sterilise medical equipment, and it's completely safe to then go on and use that medical equipment in surgery because the scalpel hasn't itself become radioactive. Despite the associated dangers, radioisotopes can be really useful, and you need to know about a couple of key things that they can be used for. The first one is using them as a radioactive tracer. So in other words, something like trying to identify where in someone's heart a blockage is. So the idea is that an isotope that has a short half-life is injected. It needs to have a short half-life because we're going to detect the radiation coming out of the person's body, and that radiation is only released when a nucleus decays. So if it had a long half-life, we'd be waiting for a very long time. So that isotope is injected, it's allowed to circulate around the body, and it will collect in the damaged area or collect behind a blockage. And then a PET scanner can be used to detect the emitting radiation. So as well as having a short life, that tracer is going to need to be releasing beta radiation or gamma radiation. It's no good to have it releasing alpha radiation because the alpha radiation would be stopped by the person's skin. And so even though it was being released, we wouldn't be able to detect it. Then in radiation therapy, gamma radiation is used to kill cancer cells. And the way that they avoid damaging the healthy cells is that they basically have a sort of focused gamma ray gun, which will fire the gamma rays from various different angles. So we'd start off over here and then rotate around and fire from here and then rotate around and fire from here. And even though the cancerous cells in the tumour are being hit multiple times by those gamma rays, all of the surrounding cells are only being hit some of the time, so they're receiving a much lower dose and therefore they're much less likely to be damaged. The final part of GCSE Physics Paper 1 is about nuclear fission and nuclear fusion. So nuclear fission is the splitting of a large unstable nucleus like uranium or plutonium, and it very rarely occurs spontaneously, so just on its own without us doing anything. So in order for us to be able to actually harness this and say generate electricity, what we do is we trigger that fission reaction by firing a neutron at an unstable nucleus, and that will cause it to absorb the nucleus and then to start breaking down. As that parent nucleus undergoes fission, it splits into 2 smaller daughter nuclei, which are about the same size as each other, and it also gives off 2 or sometimes 3 neutrons, plus some gamma rays, and also some energy is released. All of the different particles that are released from this, all of the fission products are moving, so they all have kinetic energy. At the start of this nuclear fission process, I provided 1 neutron, which caused 1 parent nucleus to decay. But that parent nucleus is going to produce up to 3 more neutrons, and so in the next round, we can have 3 more nuclei decaying. And then we're going to end up with 9 neutrons, which can cause another 9 nuclei to decay. And you can see how very, very quickly this can escalate, and this is what's called a chain reaction. In a nuclear reactor, that chain reaction is controlled in order to control the amount of energy that's being released. But in a nuclear weapon, or when there's a nuclear accident, there's an uncontrolled chain reaction. And this is what happened in Chernobyl and caused a meltdown. So to prevent this from happening, there are things called control rods, which are made out of boron, and they are able to absorb any neutrons. And when the core starts to get hot, the boron control rods are lowered and they absorb any neutrons and slow down this whole process. And then when the reaction is slowed down too much and everything starts to cool down, then the control rods are raised above the fuel rods again so that the neutrons can carry on interacting with those parent nuclei and the reaction can start to build up again. In contrast to nuclear fission, where large parent nuclei split to make smaller daughter nuclei, in nuclear fusion we see the reverse. Small nuclei like hydrogen fusing together to make larger nuclei like helium, and this is one of the first fusion reactions that occurs in stars like the Sun. Now, when this happens, it releases significantly more energy than fission, and we would love to be able to harness this to use for making electricity and things, but it's not possible for us to do this safely on Earth at the moment because it needs a really high temperature and a really high pressure to start and also to contain the reaction. Now, you might be thinking, well, if it's impossible to do, then how does an H-bomb exist? How does a hydrogen bomb exist? But what a hydrogen bomb does is it uses a fission reaction to create a really high temperature at the start, and that allows the hydrogen fuel contained in the bomb to fuse together to then do this fusion. But of course, at this point, we're not really worried about it being safe because it's a bomb. Its whole point is to create this devastating explosion and release a huge amount of energy. Thank you very much for watching, and I hope you're now feeling slightly better prepared for your GCSE physics exams. If you did find this video useful, then don't forget to like, subscribe, share the channel, and let me know in the comments below. And I'll be back soon with some more GCSE science revision videos.